Okay, so today I want to talk to you about interaction, light-matter interaction, but towards another application which is somehow related to the application that Yanchi also discussed, which is developing sensors based on advanced functional materials for Internet of Things. Most of you, I suppose, know what Internet of Things is, which is basically the idea of developing an intelligent interactivity between humans and things that have been functionalized with sensors able to give you a feedback in real time about some specific parameters. As you see, there are many aspects that are relevant for this Internet of Things roadmap, but we will focus, given our expertise, material scientists and physicists, on the development of sensors. Then there is a lot of work on electronics without data analysis and data handling, but we're not really focusing on that. So we're really thinking about how to develop sensors. That is why we need advanced functional materials, because we can tune the functionality of a specific material thanks to its properties, as we are physicists or material scientists or chemists, by changing the arrangements of atoms and molecules. And it's really surprising, it was surprising to me, how you can really change the properties of the material completely. Another target that we have, and that I will focus on, is the wearability of these sensors. Because of course we are targeting, if we want to functionalize and sensorize things, including our human body, we want sensors that are non-invasive, very thin, very low power operated, and that costs very little. That is because we will need large numbers, and very likely they are disposable sensors. We also need real-time readout and remote control. So there's quite a lot of requirements that some of them are far from the material functions, but not all of them. Now, what are the material platforms that we can use to develop thin, flexible devices, possibly also fabricated onto large areas, so that we can either print them, fabricate them onto large areas and then cut them out, or really cover large areas. We have, these are the major ones, but there are many more, but these are the most promising ones. We have perovskites, organic semiconductors, and high mobility oxides. You see from the green, if you see here, anyway, they're all solution deposited. That is the key point. We are now working with functional materials, semiconductors or semi-insulators, as the ones we actually discussed about, that are deposited by solution. That is, of course, a key step to implement very simple, low-cost deposition. I will focus today on perovskites and organic semiconductors, but the same applies also to oxide semiconductors. When I say the key point is solution deposition, because they can really be fabricated by inkjet printing, like the standard inkjets that we use for paper, or slightly more complex. Here is a typical inkjet printer. And we can fabricate electronic circuits onto flexible, non-conventional substrate by printing these solution depositable semiconductors. You can see that is quite a change and provides the possibility of developing, that is, for example, a 2D matrix of pixels that are electronic transistors. Just a very brief comment that will tell us a little bit more about why we want to go towards printed and flexible electronics, because the business will be very much interested in this. So there is quite a lot of interest also in the industrial market for this type of sensors. We are more interested in the physics of it, to be honest, and that is why a lot of scientists that are working on very different areas of these flexible electronics are inventing sensors and materials that allow to sense different things. Here you see examples of transistors that can be tattooed onto your body to monitor your temperature, your glucose level, and many other different information. But also, you can, as we discussed here, put your sensor on an item. For example, here is a diaper for a baby, to monitor if it has been wet or not. So that is the Internet of Things idea. You sensorize items, common life items. So what I want to tell you about today is not the whole story about flexible electronics, but I will focus on sensors that are flexible. They are electronic sensors, and they detect high energy photons. So we are still talking about light-matter interaction, but ionizing radiation. So we are moving into X-rays, not visible light. And here is the spectrum that you see before. I think it's exactly the same. I knew I had it. I did it from another presentation. And we are moving into the X-ray area, okay, range. So no more visible or UV, but X-rays. Why do we need X-rays? We know that we are surrounded by X-rays. Medical applications, security applications, cultural heritage, airport security, nuclear industry. So we need to monitor ionizing radiation around us. How do we do it? We have two typical geometries: indirect detection and direct detection. The indirect detection is based on a two-step process. X-ray photons hit on a material which is called a scintillator that is capable of changing the energy of the photons, downgrading them into visible photons. What you do, you transfer these photons by simply coupling the scintillator to a photodiode, which is a device that is able to detect visible photons. Okay? So that is the indirect. The direct detection is based on one step. You have a material, which is a semiconductor, capable of directly detecting X-ray photons and converting them into electrical charge carriers. So an electron and a hole. That is what I will focus my talk today. So we are developing semiconductors, organic or perovskites, deposited by solution onto large areas, capable of detecting high energy photons directly. Why do we need to do it, and can't we just use the standard inorganic semiconductors like silicon, gallium nitride, or cadmium zinc telluride? Because all of these materials have some drawbacks. They work very well in some respects, but again, they cannot be deposited at low cost in a sustainable way and onto large areas. When I say in a sustainable way, I really mean that when you print these materials, the one I'm talking about today, you really use what is called a bottom-up deposition method, and you deposit a few hundred nanometers of the active material, exactly what you need. You don't waste any material. You use low temperatures, room temperatures, and that is completely different from what happens even with silicon. Silicon, which is the basis of every electronic device you use every day, it's very expensive to fabricate, not in terms of cost, because now the industry is established, but in terms of sustainability, it uses a lot of chemicals, and a lot of energy is required to produce it. So we need to go a bit further. And that is what you get with these organic or hybrid semiconductors. These are all the advantages, and in green, I have highlighted two typical advantages of the organic ones. They are biocompatible, and they are human tissue equivalent. What does it mean? It means that when they are hit by an X-ray, the X-ray basically sees a material which is very similar to the human tissue. Why is it relevant? It is relevant for medical applications. Because in medical application, you really want your detector, if you want a detector to be placed on your body when you do an X-ray scan at a doctor, you really want the detector not to absorb too much radiation or make it change its structure, its energy, so that when it hits your body, it's not what it's meant to be. So that is exactly one of the targets we have developing this 2D pixelated matrix that can be fabricated onto flexible matrices, a flexible substrate, and be used as direct detectors during an X-ray scan. Now, that is one of the application of the ALGO. Why are organic and perovskites so studied? Because if you look at this graph, you see how the performance of these detectors has increased over the last years, and you see that the study really refers to the past few years, and you see that orange are the perovskite and blue are the organic. The dotted lines that you see are the polycrystalline, CZT, and the amorphous selenide, which are the inorganic standard material used for radiation detector. So you see that these new materials, despite all these low cost and very easy fabrication methods, are really promising. Now, what are the basic principles of organic materials? They've been discovered recently, and they're based on the presence of carbon atoms. They're mostly composed of carbon, hydrogen, and oxygen, so that's why they're called organic. And they exploit the presence of single and double ligands between carbon atoms. Basically, I don't want to go too much into that, but basically they exploit the combination of pi orbitals, I don't know if you studied them, and that produce a delocalized orbital very similar to the conduction band Bianchi was discussing before. So with these materials, you create basically, either with conjugated polymers or with small molecules, small conduction bands, one attached to the other, that allow this material to transport electrical charges as if they were inorganic semiconductors. One more information, given their very typical behavior, we can use them to fabricate transistors in a similar way to what we do with silicon, but they have some properties that make them peculiar. A transistor is made of three electrical contacts, source, drain, and gate. We need a semiconductor active layer, which is made of the organic thin film, and a dielectric. What happens when you apply a bias to the gate? You basically attract or reorient, that's correct, the charges in the dielectric that attract, that attract charges in the semiconductor that are mobile into the channel. Once the charges in the semiconductor go in the channel, which is the region at the interface between the organic semiconductor and the dielectric, if you apply a bias between the source and drain, you get a transport. So basically, you can enhance the transport in the semiconductor by applying a gate that attracts more charges in the channel. That is called accumulation mode. Why am I telling you this? Because it tells you that in order to have a good operating organic field effect transistor, you don't need a very thick material, because everything happens at the interface between the organic semiconductor and the dielectric. And that is one of the big strengths of these materials. Because if this is a typical structure, similar to the one I was showing you before, of an organic field effect transistor, the thickness of the organic semiconductor can be 100 nanometers to have it operate properly, even less actually. So we really use very little material, and we position it exactly where we need it. How do we deposit it? We use inkjet printing, nozzle printing, if we want to be more precise, or bar coating, which is using a bar to spread the liquid, the solution of the semiconductor, over a large area. What is the advantage of bar coating? That you see you can use patterned substrate already with all the electrodes. You coat the solution, and suddenly you have a matrix of, for example here, you have 20 transistors. Each one, you see the zoom, is composed of electrodes and microcrystalline, very thin organic layers. Now, how do we study them under X-rays? We use different types of X-rays, mostly a molybdenum tube or synchrotron. We choose these energies because these are typical for medical application. These are typical for mammography application. So we want to make sure that these materials and these devices are operating well under actual operating conditions. Here is an image of the film that we deposit. On the left-hand side, you see the drying out procedure when the solvent of the solution evaporates, and it leaves this microcrystalline structure. Each crystal that you see imaged in an atomic force microscope, in both, in the bottom one, the top one is an optical microscope. You see that the dimensions are thickness about 100 nanometer, length about 100 micron. So they're really thin, multiple crystals. The molecule we're using is called TIPS pentacene. As you see, it's based on carbon, hydrogen, and silicon. It has 2 silicon atoms. These devices are definitely flexible because they're so thin. And what is interesting, they respond very nice to X-rays. So, X-rays on-off, you see an increase in the current measured between the source and drain. Very clear increase. We call the delta I the increasing photocurrent. 2 important points. This delta I is reproducible, stable, and we can extract the signal at 0.2 volts. That means if we want to operate this device, we really need very, very low power. Typically, a very good inorganic detector that operates and gives you much more information than this one may require up to 100 volts to be operated, but it tells you more. But it's not really easily there. The delta I, this photocurrent, is typically reported as a function of the dose rate, which is the flux of photons that is hitting the sample. So we change the flux of photons. And if the line is linearly increasing, we can say that this device can be used as a dosimeter because the response scales linearly with the incoming dose. The slope is called the sensitivity. And this is really interesting because it's what you need to assess the suitability of the material in the device to be used for X-ray detection. Now, the key point from the physics point of view is why does it work? Because if we rely on the standard X-ray material interaction model, we have 3 major steps. Charge generation, that is related to the absorption of the X-rays from the material. Second step, charge transport, that is related to how the generated charge by each incoming photon reaches the electrodes. There, the trapping, the trapping induced by defects in the material can be critical. The third step is the collection at the electrode. So the carriers need to overcome the barrier within the material and pass onto the electrodes that are typically made of metal. If we look at these 3 steps, now forget about all the calculation, but what I'm showing you is the 3 steps process. If we calculate what we should see in these thin films of organic material, we would collect a current which is less than 2 picoamperes, which is not good because we are actually collecting a current which is of the order of nanoamperes. So that means that this model is not working and that something should happen because in principle these materials so thin with such low atomic numbers should not be able to absorb any X-rays. Why are they working? They are working because what happens is a photoconductive gain process. So here the defects and the traps at the interface of the thin organic film and the dielectric of the substrate play a very important role in trapping one of the 2 photogenerated carriers, typically electrons. So the X-ray generates holes in the electrons stay trapped, and the hole to maintain the charge neutrality, more holes must be generated and collected. That is why we are collecting an extra current through a gain factor that is related to the trapping effect. This trapping effect ceases immediately once the irradiation stops and the traps re-emit the trapped electrons. So this photoconductive gain is the key point that we need to study in order to control and enhance the X-ray detection from our materials. The photoconductive gain is present also in other materials under visible lights, but under X-rays was a bit of a novelty. And it is interesting because the photoconductive gain is based on two parameters, the transit time and the carrier recombination lifetime. If we control either the geometry of the device and control the transit time, or the defects in the material and therefore the carrier recombination time, we can modify the gain. And if we modify the gain, we modify the collected photocurrent, which is our output that we want to maximize. This is probably more clearly stated here. You see the photocurrent, gain times collected current, which depends on these two, carrier lifetime and recombination lifetime. In order to increase this photoconductive gain effect, we can operate on the transport properties. You see, it depends on the mobility. We can operate on the absorption of radiation, because the greater the atomic number, the greater is the stopping power for X-rays. So we can change the molecule, because chemists are very good in modifying these solution depositable organic molecules. Or we can change the device architecture. So basically, if we work along, we have many parameters that we can play with in order to maximize the direct detection. Here is an example of similar of device architecture. It could be the OFET I told you about, but even a simple two-terminal structure can be good. And here is an example of a matrix of 2D pixels fabricated onto flexible substrate. Indeed, there are advantages of using transistors. Here are examples, but the structure is more complex. So the fabrication requires multiple steps. So sometimes it's better to rely onto a simple two-terminal device, because maybe you don't need this particular performance. What I really want to comment lastly is the role of defects that we can control by controlling the morphology of the thin film. Here I'm going to show you how, by controlling the speed of this solution deposited organic thin film, we can change the morphology of the grain of this polycrystalline film. You see clearly, these are two devices. The metal strips are the source and drain contacts. We call them interdigitated. You see, they're like fingers of two hands, one inside the other, deposited at two different speeds. You see that the grain shape and size is different. But you see it more clearly in this atomic force microscopy image. Then you see that by increasing the speed, we reduce the grain size. If we reduce the grain size, look at the photocurrent. The photocurrent increases, given everything else identical. Why is it so? And if the photocurrent not only increases, but the slope increases. And we know that the slope of the photocurrent versus the dose rate is the sensitivity, which is a very important figure of merit of our detection. So why is this interesting? Because we understand and we validate the role of traps. Because if we have smaller grain, what happens is that we have more interface between one grain and the other, and it is at the interfaces that the defects are created and are active. So if we have smaller grains, we have more defects, and that is why the photoconductive gain increases, and we have a higher sensitivity. So that is just to say that we can play around with many parameters thanks to these functional materials to impart the properties we believe are needed for the application of the X-rays. One last comment is about the atomic number to increase the radiation absorption. How do you increase the radiation absorption? By increasing Z. We have organic molecules, as I said, carbon, hydrogen, and 2 silicon atoms. If we simply change 2 silicon atoms with 2 germanium atoms, the atomic number increases, and the molecule is still working as a good semiconductor, still responding well to X-rays, and the sensitivity is increasing. In this case, we're not working on the defects, but we are working on the absorption coefficient. Okay? Last, I don't know if I still have time, otherwise I will continue. Okay. Last, just to give you more information about other functional materials that are good for this application, I would like to just tell you something about perovskites. I think Daniela tomorrow will tell you a little bit more about perovskites, so I will not discuss too much about the structure, but they are very interesting materials used for solar cells applications. You see highlighted in red the very impressive increase in performance of perovskite-based solar cells in the last years, and that is not an updated graph. Perovskites are compounds based on the ones I'm talking about are hybrid, so they are organic and inorganic, and they have a very high attenuated fraction for X-rays because they contain heavy atoms, for example lead, and they really stop X-rays very nicely. Not only, but they have a very good carrier transport properties, which are very good for the second and third step I mentioned you. So they're very good at generating charge under X-ray photons, transporting it, and collecting it. Now, thanks to what has been done with solar cells, we can exploit it. And we can use all this knowledge to create X-ray detectors that are different from solar cells because they need to be active under higher energy photons. Still, we can use a typical perovskite solar cell structure that you see summarized in the round, in the circle. You immediately see that this is more complex. So it's an heterostructure with multi-layers, okay? Because perovskites are more delicate in a way. They're very functional, but still a bit more delicate. So basically here you see a structure where you have the perovskite in the middle and some layers on each side that help in creating an electric field capable of extracting the carriers that are generating and at protecting the perovskite from degradation from external agents. Indeed, we can fabricate very thin and flexible devices because everything is really very, very small. The thickness of the layers, active layer, is still about 100 or 200 nanometers. What do we get as a response under X-rays? Okay, here you see 3 different parameters. Sensitivity, we discussed it. And you see added the dark current and the limit of detection. That are the other 2 important figures of merit of a radiation detector. So sensitivity is the photocurrent as a function of the dose rate. Dark current is, as the name says, the current that you measure without any external stimuli. It has to be very low. Why? Because the lower the dark current, the easier it is to detect every single minor event that occurs. Okay? So the delta I over I becomes bigger if the I is really small. The third is the limit of detection, which is the smallest signal that you can detect. Of course, ideally, you want all these parameters to be optimized. But very often, you don't really need all 3 of them. So what I'm showing here is that on the Y scale, you see how, by changing the type of layers that you use to couple to the same perovskite. So here I'm using the same active semiconductor, but I'm just changing the interlayers that help creating the diode structure, so the photodiode electric field, and to collect the charge carriers. By simply changing their combination, look at how the response and the properties of this device can change. So again, what I'm saying is that the material is very important, but also the interfaces and the structure of the device that you fabricate have a huge role. And you can play around with them and identify novel and, again, very often unexpected performances. Here is an example of 3 of these structures. You see the perovskite layer is the same in all of them, but what changes are the very thin, few nanometer thick interlayers that are used as electrodes. Hole transport layer or electron transport layer that collect the hole or the electrons, respectively, photogenerated inside the perovskite. You see that all these 3 work very well. Look at the nice on-off response to an on-off X-ray beam. You see clearly when the beam is on and off. The response is sharp, fast, and reproducible. What is the difference? You see already the intensity, but if we plot the delta I over the dose rate, you see that one of them has a definitely higher slope, the central one. So this one has a much higher sensitivity than the other. Unfortunately, as I showed you in the previous graph, this does not bring also the best dark current and the best limit of detection. So often you will have a trade-off between this parameter, or somebody will have to find another material or another combination that is able to get all 3 parameters at best together. Another suggestion for future material scientists is that you can combine and invent novel materials. Here what we're doing is combining perovskites, methylammonium lead iodide, with a polymer, with an organic material. We make a blend. And we deposit it, our solution, onto electrodes. So it's a very simple 2-terminal device. This image you see is a cross-section in a scanning electron microscope that shows, you see, the very messy top layer and the substrate. Still, the material is messy, but it's not amorphous. It's a polycrystalline film that has a very good transport property, very good enough transport properties to grant you, you see, a nice photocurrent to an on-off X-ray beam at very low operating biases. Okay? And the sensitivity is also very good at high energies, so up to 150 kilo electron volts. So, to conclude, I really think that there is a lot that we can do on perovskite on organics, and a lot of researchers are working on this, as you saw, in the past 4 or 5 years. There's been a lot of work on that, because the performance of these materials is really well beyond what I call the state of the art that I showed you, the materials used for large area radiation detection. And to conclude, I really think there is a lot of physics and chemistry going on here that goes from the preparing the solution of the material, working with the transistor or the device geometry, depositing it with different procedures. Now we have already quite a variety, but many more can be envisaged, controlling the morphology of the material and correlating the electrical properties of the material to the photon-matter interaction that is the core of this sensing action that we are targeting with this material. So I really think there is a lot of research needed on these materials that are very promising, given all the comments that I made before. So I really encourage young students not to work on these in specific, but to really see how wide the field of advanced functional materials can be. I think I will stop here. Thank you.
have a couple of questions actually. One of them is you said that you can have layers between.
Yeah.
Sorry. Okay, also one layer, but what about the dielectric layer you have on the
Okay, if you want to make a transistor, that's a very good question. The dielectric should not be too thick anyway for two reasons. First, because you want to maintain flexibility. And second, because you don't want it to stop too much the radiation. So typically the dielectric thickness can be 10 nanometers. So they're really thin layers. They're made of beryllium, for example, which is another organic material, or aluminum oxide, which can be spattered or deposited again by solution, but they are very thin. You don't want them too thick, otherwise you will need to apply even higher voltages to operate the device. So you need thin for low operating bias, flexibility, and no radiation stopping.
Does that not give like fluorine-related fluorine?
That's a good question, but that's why you need to operate with very good dielectric. No, seriously. But if you're good enough, and typically now the technologies are good enough, you can deposit 10 nanometer thick layers that are with no holes and no leakage. And so the technology allows you to do that.
Another question was about actually about flexibility, because you have talked about air type and dielectric, and I don't know if you are fairly with crystalline or
Good. Very nice. Okay, so here are the backup slides of mechanical flexibility. I knew it was coming. So what we do the test by bending one time and multiple times. So what we notice, which I think is very interesting thinking about the crystalline nature of the film, is that flat is the first measure, the black. Then we do one bending, then we measure it again, and we see that the performance has changed. It's the right one. Then we keep bending, and we bend it 100 times, you see in the other graph, and the performance stays the same. So it's the first bending that makes a difference. So we said why. And let me see, I had it somewhere. Aha, here it is. We did some tests by under atomic force microscopy in the Kelvin probe force microscopy mode. Well, anyway, we looked at one crystalline that crossed between the source and the drain, and we bent it. The atomic force microscope is able to tell you information, look at the sizes, onto very, very small sizes. And with this mode, we are measuring, look, on the left-hand side there is the source. On the right-hand side you can see the strip of the drain. We can measure the electrical bias applied across the crystal. So when the crystal is flat, you see that we are applying 0 volt on the source, look that it is red, and plus 5 volt on the drain. And you see that the bias scales nicely, meaning that there is a very good connection. If we bend it, and we do the same experiment under bending with the atomic force microscope, that is what we observe. We observe that if we bend it 0.6%, 1.4%, or 3%, I'm sorry, this is not the bending, it's the strain that is applied on the material, we clearly see that when we get to 3%, there's no contact anymore between the source and the drain, or the device is not properly connected, the crystal is not properly connected. So the idea, we checked it better, is that we get micro cracks or nano cracks in the crystals that propagate through the crystals. But what is the good message? That given what I told you before about organic devices operating only with the carriers accumulated at the bottom interface, these cracks, if you don't bend it too much, do not reach the interface. So indeed, there is a decrease in the performance, but the operation is not affected. Because you see, the charge carriers, even with cracks, still are able to move freely at the interface. And that is another typical advantage of these organic thin films. Thank you.
Am I entitled to I'm not a student, but I prefer the student has got a question. So if not,
There is a student.
yeah, go on.
Then I will.
Being an organic semiconductor, what might be the problems related to rising temperatures?
During operation or during fabrication?
Both. I mean the limits due to temperature.
With the organic?
Yes.
Okay. Okay. Yes. Organic semiconductors are not happy at high temperature. So that's the, as always, there is the good side and the bad side. So the good side is that you can deposit them at room temperature. And so you can use substrates that do not tolerate high temperature. But the bad side is that you cannot put them at high temperature. And high temperature, for example, is above 100, 150 degrees centigrade. So it is a temperature which is very good for normal operation in our life. But if you have to operate them in a furnace, forget it. Okay, they will melt. So there is a high temperature limit.
Thank you. Very, very nice talk. And being myself an organic chemist,
I'm afraid of your question now.
I would like to know why TIPS pentacene. I have a lot of dyes we have prepared in my group over the last 20 years, and I wonder, would any one of that would be useful for X-ray detection? What are you looking for into the TIPS pentacene?
Okay, we started with TIPS pentacene for two reasons. First, because it was the most popular one and tested one as an electronic grade semiconductor, organic semiconductor. So we wanted to use something that was fully characterized and that we could rely on in terms of mobility, interface control. So we didn't have to worry about that. And everything that we would see, we were sure was related to X-ray. Then the second question is very interesting. That's why we started changing the molecule. Because of course that is not the best. It's just one of the semiconductors. So we need, if I was to ask my wish list would be low dark current. So a semi-insulator, but good enough to grant charge collection. Okay? As crystalline as possible, because the charge transport needs to be good. But that's not a clear request. I will formulate it better. Because we could also think about blends, where you have, and the third question would be a high Z for X-ray stopping power. So the idea would be either the molecule has a high Z and packs nicely, or a blend with high Z nanoparticles, centers, and that are able to nicely transfer the charge to the matrix that can then collect it would be a very nice solution as well. So these are some of the, and if I may add, since he's here, I would love to have a boron-containing molecule for neutron detection. So in case you have anything boron-related that is transport, I mean an electronic material.
We have some boron containing.
So we will talk. We will talk. That would be very nice.
I wonder, is the TIPS pentacene stable under oxygen? Because I guess the
under oxygen.
Yeah, under air. I mean regular air. Can you operate? You need to cover it.
No. We operate them in room and light. They're okay, honestly. They're not too bad. They're more stable. I don't know if you know Marta Mastorren at the ICMAD in Barcelona. And we did with her a blend of polystyrene and TIPS pentacene with the bar-assisted coating. And the polymer blended with the TIPS pentacene was found to stabilize it because it kind of seals the top. And so we kind of have an intrinsic, I didn't go into the details of all this, but the idea is that if you do a proper blend, you can even stabilize it further. But it's relatively stable. again, you don't think you will use it for a year. And also the difference with the solar cells is that they don't need to be under the sun, under the rain. So that's a big difference. So they stay indoors, they are, and you can also seal them. So you could envisage a protection if needed. But so far we did it for a few months.
Okay. Thanks a lot.
Yeah, just, I mean, not a long time.
Okay, thank you very much.
Thank you.